I would like to talk about the methodology for FDM 4D printing with thermo-responsive shape memory polymers. My name is Ferdinand Cerbe, and I'm from the Technical University of Braunschweig, and I'm currently working at the Institute of Mechanics and Adaptronics. So shortly about the motivation that we had creating this methodology to describe FDM 4D printing. And the motivation came from, we have a simple bending transformation, but we had a complex structure to describe. And in order to create a transparency of our research results and the reproducibility of our research results, we wanted to make sure that we didn't forget anything and document our methodology. And lastly, it also gave us the opportunity to identify missing information that might be interesting, and therefore we identified new research areas. And with that said, today my talk is partly referring to the chapter that we wrote in the volume 2 of Smart Materials in Additive Manufacturing, edited by Madi and Ali. Thank you very much. And I would like to start with this, with this short video. On the left side, you can see, yes, on the left side you can see a top view of a structure, and on the right side you can see a thermal imaging, a side view of a thermal imaging camera. And in the video, you can see that the material heats up and our structure deforms at roughly 60 to 70 degrees Celsius. And by that, you probably already understood how the transformation works. It's a simple bending transformation. But now I would like to go into detail how to describe the structure. And we can start describing the structure with the 4D printing basis. And those allow us to classify or cluster our research results. So I'd like to start with a smart material, which in our case is a thermo-responsive filament. And we use a 3D printer, in our case an FDM printer, and certain mathematics to predict our transformation that we will have. So with those, this leads us to a smart static structure, which comes in a temporary shape. And this temporary shape then can be, a stimulus can be applied. In our case, this stimulus is temperature, and with a certain interaction mechanism, which is a thermomechanical, we will have a smart dynamic structure. In our case, our structure will transform from the temporary shape into a permanent shape. So we developed this process model for additive manufacturing, or our methodology to describe it. And we start with the material selection. So we have a certain shape memory behavior, which can be seen here. And this shape memory behavior can be described with different parameters, for example, the transformation temperature, forces, or the magnitude of the transformation. And then we have certain material properties that we can describe, for example, the complex modulus, rheological properties, or the glass transition, and the melting temperature. And when we've decided, or when we've selected a certain material, we come to the structure design, where we have to have in mind a certain type of transformation that we're aiming at. And this will be defined by the layer composition that we have to choose accordingly, the printing direction, and the manipulation parameter, which I will go into a little bit later. So this can be supported by a forward or an inverse simulation, where on the one hand, we have a set of parameters that we have, that we give in our process, and we want to find the transformation. And on the other hand, we know what transformation we want, and we want to find the parameters. So this might still sound a little bit complex, but I'm going into the more visual part in 2 slides. So when it's coming to the printing with FDM, we have to describe a certain operating condition, and this operating condition includes all the parameters that we put into our FDM printer. And this is mainly, I mean, those are a couple of parameters that I name here, but they go beyond those 5 parameters that I mentioned here. So, but very important ones that already were investigated are the printing speed, the nozzle temperature, the layer height, the bed temperature, and, for example, the cooling rate. And lastly, after the printing, we have this smart static structure, and with the activation, we come to the smart dynamic structure and transform to the permanent shape. And for the activation, of course, we also have activation parameters which include the stimulus magnitude, for example, the stimulus duration, or the stimulus medium. And lastly, we have to consider certain interferences that we might not be able to eliminate, but we can at least try to describe them and reduce to a certain degree. So the shape memory behavior is for shape memory polymers, or for thermo-responsive shape memory polymers, often described with this shape memory cycle that we can see here. So we're starting at a low temperature, below 45 degrees, and we're heating our structure up to a certain high temperature, in this case, somewhere around 80 degrees. And by heating it up, we have a certain coefficient of thermal expansion, and we will come out with a certain strain here, positive strain. So after that, we can stretch this sample and cool it down. And in this controlled environment, those endpoints are very, very defined. And with those 2 steps, or those 2 procedures, we're coming up with a programmed step, with a programmed sample, and all those 2 steps we can call the programming step. After the programming step, we will end up with a certain strain at a low temperature, below our transition temperature, and from there on we can start the recovery of our sample. And in this case, you can see that the strain of about 5% we can recover to a certain degree. Further material properties of interest are in FDM printing, the viscosity of the melt, for example, the complex modulus of viscoelastic and elastic, or of the complex modulus of the material, and certain thermal transitions, which might be the melting transition or the glass transition temperature for polymers. So the main questions that we have to ask ourselves in the material selection are: at which temperatures are the different shapes needed? So I heard it in this question yesterday in one presentation. Yeah, can you modify the transition temperature to a certain degree? Or even in the last one, it was said that the glass transition temperature is reduced. And this can be, of course, an advantage or a disadvantage. Always depends on what your application is. And then the second question would be, what forces are needed to change this shape? Or what kind of forces can we expect to change this shape? So with that, we can follow up with a structure design. And when we have an aimed type of transformation, I already said we have those 3 different areas: the layer composition, printing direction, and manipulation parameter. So the layer composition pretty much defines what layers are the layers of shrinkage, and often used are those passive and active layers. So passive layers are layers which remain almost constant in length, and active layers either shrink or expand upon activation. So then the printing direction defines in FDM 4D printing the direction of shrinkage. So if we, for example, consider a 0 degree direction, then in this direction also our shrinkage will be. If we use a phi direction, then in phi direction the shrinkage will be, and therefore we can model certain transformations which might result in helixing or similar. So, and lastly, we're coming to the manipulation parameter, which is the amount of shrinkage. So the manipulation parameter doesn't have to be the printing speed, which is written down right here on the slide, but the printing speed is often used in literature because it was shown that it's easy to modify during printing, and it has a very good relation in a certain area, which can almost be assumed to be linear. So with different manipulation parameters, of course, you can also achieve different results, but those are the main categories where you have the structural design in. Then I would like to come to the printing, to the actual printing. And as I said, the operating condition is defined by all the parameters that go into the printing process. And there are certain slicer-specific operating conditions, which might be, for example, the printing speed, nozzle temperature, and layer height, and of course, a lot more. And then you also have certain printer or hardware-specific operating conditions. So those printer or hardware-specific operating conditions could be nozzle size or material, the filament liquefaction, and the build platform material. And to illustrate the influences, I would like to discuss this programming procedure during printing shortly. On the left hand, we can see the nozzle where material is extruded and cooled down. And here we can see the shape memory cycle related to this picture. And in the first step, we're just having, in the first state, we just have cold material at room temperature maybe, and the material is unstrained so far. So then we're feeding our material into the nozzle, and therefore we're heating up our material until it becomes first over the glass transition temperature and then over the melting temperature. So we have a certain viscous melt in our nozzle here. In the next step, our material, and this is the most complex part of the whole diagram, the material exits the nozzle, and somehow, of course, now we don't have this controlled environment, which I mentioned in the shape memory cycle before. Now we have a more complex environment. So the cooling and the stretching occurs at the same time, and therefore we have this stretching and cooling step, not in like a rectangular manner, but in like a more curved manner. And lastly, we will have our programmed state, which is a cold state and with a certain strain implied. So after that, only the activation comes to last, and the activation parameters, as I said, are magnitude, duration, medium, and interferences. And the magnitude in our case, if we're talking about heat, is or should be described in the temperature, either degrees Celsius or Kelvin. And then we have the duration that our structure is exposed to this stimulus, and this can be described in seconds or in minutes. But it is always very important to describe the procedure very precisely, because those two parameters strongly influence the recovery behavior, for example, the speed and the absolute transformation range. So then we're coming to the medium, and the medium is something that so far hasn't been investigated as much. So this might be a new research topic which could be interesting. So of course we could either apply a certain gaseous medium to our structure, a liquid or a solid medium. And with gases, I mean, we could put our structure into an oven and therefore heat up the air, the surrounding air in the oven, and activate our structure. Liquid, we can use different liquids. And with solid, this is the one we used in the structure I showed you in the beginning. We used an electric heating element, which is inside the structure and therefore heats our structure from inside. Lastly, we have certain interferences. For example, the interference of gravity can often not be neglected, so you somehow have to find a way to reduce the influence of gravity, for example. So now I would like to describe the example structure which I showed you in the beginning. And I will start by just showing you that we have two active layers PLA. We have one passive layer of PLA, one conductive layer of conductive PLA, and two active layers of PLA. And here's a structure that we designed in that case. And with the lines, with the black lines, you can see the printing direction. And maybe how you can identify right here, we will have a bending hinge, which is mainly where the main transformation lies within the middle of the hinge. So on the conductive layer, where the heating comes from, we applied silver ink, which should reduce the resistance in those two areas, because we want to focus high resistance areas inside the heating area. And on those sides, we wanted to reduce the resistance so far that we have a better performance, better heating performance. So those are printing parameters, and I don't want to go into detail about those printing parameters. Of course, you can read them in the chapter. But we have three different materials: active, passive, PLA, which only differ in terms of the parameters that the slicing parameters that we put in. And then the conductive PLA also had different settings because we investigated that we have the best performance of our heating element. So the activation temperature, our medium, was this electric heating element, which I described. The magnitude, we derived a voltage which we applied from a 2 watts power input, and at the same time we measured the temperature in the first steps, even with the thermocouple, and then later we could rely on the thermal imaging camera. So the duration was here applied for 300 seconds, and interferences, we try to reduce the effect of gravity by having gravity perpendicular to our bending transformation. So to not lead you with only the methodology into this Friday evening, I will also want to show you some new results that we acquired. We changed the nozzle sizes, and from 0.25 to 0.8 millimeters. And here on the side, you can see the transformation of the 0.4 millimeter nozzle and the one from 0.8 millimeter nozzle. And you can see that the performance of the 0.8 millimeter nozzle is better than of the 0.4 millimeter nozzle. Furthermore, the force also increases, which is also expected, because when we have a larger deformation and we block this deformation at the initial state, at the printed state, then we expect a larger force. Lastly, we have the certain resistance here, which lies somewhere around 1.5 to 2 kilo ohms, and the nozzle of 0.8 millimeters also showed the lowest resistance in our case, which is beneficial because then we can apply lower voltage, and therefore and therefore the risk of any hazard is reduced. So on the bottom right, you can see that we also derived the flow rate during printing, which we thought might be an indicator for the transformation angle that we can see here. So with that, I would like to tell you that for us, the standardized process led to more transparency and better reproducibility of our research results, and the coordination within my group was a lot better. And of course, the identification of new research areas and easier planning of experiments. And this identification of new research areas also shows when I'm talking about our current project, where we are trying to investigate different filaments and therefore show that we can 4D print with them as well. With that said, I would like to thank you for your attention, and you're very welcome and invited to read the second chapter of Volume 2, Smart Materials in Additive Manufacturing. Since you already know how the structure looks like, you can just jump right to the results.